these are exponential inequalities. We actually solved exponential equations, but what you have to do to solve exponential an exponential inequality would be the same. So the same steps that you would follow in order to solve an equation. When you solve an equation, you try to isolate x. Here also you have to isolate x and finally get an inequality only for x. So the steps that you would be doing would be the same. You try to bring the x down. Yeah, so in some you have double inequalities, but still it's the same. So what I will do is there a lagging today? Is there a lagging between the voice and the visual? My thumbnail? Clear, okay, okay, happy. I'm seeing a lag. My own thumbnail on my screen is lagging behind my voice. It's not like synchronized. Anyway, if it's clear to you, that's all we need, right? Okay, so let me just read out the answers. Okay, if you haven't gotten any of the answers, you let me know, then I can do them. So this first one, part one, the solution set, you get a set of values for x, right? A range of values for x. Part one solution is x is smaller than 7. X is smaller than 7. Okay. Part 2, x is greater than or equal to, you know what, I will just type it here while saying it. I will type it in the chat box so that you can see. So part one, I will just say 1, 2, 3. Okay, part 1, I said x is less than 7, right? Number two means part 2. Okay, part 2, x is greater than or equal to 3. Greater than or equal to 3. Third one, so you have to stop me if you haven't gotten the solution. Okay, stop me and ask me if you haven't gotten the solution. Part 3, so in even in part 2, now part 1, the first one is very straightforward. You have just an exponential term and just one number. You can just take log all on both sides and immediately x comes down. In part 2, you also have a number on the left hand side. You simply take it to the other side so that you have just one number on the right hand side and your exponential term on the left hand side. Whenever you have a number here, you take that number to the side where you have the number, all the numbers, right? So part 3 is x is greater than or equal to 3 again, same solution, right? Part 4, part 4, you have 0.6 to the power of x, right? Part 4 answer is x is greater than 0.437. I'm very sorry. Let me just, sorry about that. Okay. X is greater than 0.4. That's the answer for the fourth one. X is greater than 0.437. Fifth one, x is smaller than or equal to 1. Okay. Wow, you all have gotten all the answers. This is nice. Number 6, part 6, that is part 6. X is greater than or equal to 0.8 0.322, 0.322. From number 7 onwards, part 7 and 8, you have a double inequality, right? So your solution for x will also be a double inequality. X would be bounded by two things, right? All these are some number onwards or below some number or after some number, right? For 7 and 8, you will have a range bounded by two boundaries, two numbers. X is between this and this, right? That kind of a solution. So part 7, x is between 0.431. I'll write it properly. So x is in the middle. X is greater than or equal to 0.431 and less than 1.29. I hope you can read the way I'm writing the notation, because I can't on the keyboard. You know, you don't have greater than or equal to that symbol. So I'm putting the greater than equal together. That means greater than or equal to. So x is greater than or equal to 0.431 and less than, just less than 1.29. Number 8, part 8, x is greater than 1 but less than 2.58. X is greater than 1 and less than 2.58. I can also say it as x is between 1 and 2.58. If you think of a number line and visualize it on a number line, that would be more clear. And the, did I miss? Oh wait, I made a mistake. Sorry. Huh. Can I delete this? No, I can't. Number 8 is wrong. 8 is, why didn't anyone, how did I make the mistake? So 5, 6, 7, yeah. Eighth one, I'm sorry. This is the 9th answer I put as 8. 8th one is x is between 0 and it's greater than or equal to 0 and less than 0.827. I will write previous 8 is wrong or something. No? I will write that. Previous 8 is wrong. Okay, that's what 8 is. And then 9 and 10, the last two, you have this exponential inequality combined with modulus. Okay, so were you able to do those two as well? Okay, you can remove the modulus sign. You don't have to square this. I know that you might have gotten into the habit of the moment you see a modulus sign in an equation or an inequality, you may have gotten into the habit of squaring it immediately. Don't do that. We don't have to square it here because you just have a number. So what you can break this down into two, like two parts. I hope, please let me know if you want me to do it. So this means the distance between, okay. Okay, Malit, you are excused for failure. So I will just write the answer first. If you haven't gotten this, you please let me know. 9th one is x is between, it's what I wrote for number 8 by mistake. X is between 1 and 2.58. 2.58. Does anyone want me to do this? Please let me know. And the last one, number 10, x is between 0.68 and 1.49. Aha, okay, Kavindi. Which one, Kavindi? Ninth one, nah? Ninth one. Okay, I'll do the ninth one. Okay, so let me write the ninth one on my paper first. Part 9, this is part 9. Part 9 is 2 to the power of x minus 4 is less than 2. That's what you have. Let us go to the writing pad. Okay, I hope you can see it. Right? Now, the first thing you have to know in order to do this, solve this inequality is this thing. Let me write it on the side here for you to know. You remember this, if I say that some unknown number x, I'm going to write a similar inequality, but instead of the index number here, number in an index form, 2 to the power of x, let me just say x, okay? If you have modulus of x minus 4 is less than 2, what does this mean? Remember, we learned this when we were in modulus lesson. What can you say about this unknown number x? This means the distance between 4 and x. So you just think of a number line. Mark where 4 is, okay? Say this is, you have 4 here. The distance between the unknown number x and 4 is less than 2. This means distance between x and 4 is less than 2. Where could your unknown number be? So it should, at most, it can be 2 away from 4. That means 6, or to this side, 2 away from 4 up to 2. If it is less than, if the distance from x to 4 is less than 2, it can be anywhere here, but not here. It can't be equal, but anywhere in between, right? So here you can say that x is between 6 and 2. You remember that? This is from modulus knowledge. Okay, that's how you would solve that simple modulus inequality using the meaning of this expression. I didn't do any algebraic computation. I just drew a diagram and I thought of what this means. Always go down to the meaning. Okay, it always makes things simple because you're actually thinking about what it means without just manipulating symbols, you know, just throwing them to left and right and doing blind algebraic manipulations. You're actually thinking about this to get the solution. See, I just drew a little diagram and got my answer by thinking about what this means. So what you have here is the same thing. Your unknown is in the power now, but now this is some number, right? 2 to the power of x. When x takes some value, 2 to the power of x, that is an unknown number. And I know that the distance between 4 and that number is less than 2, same thing, right? So what I can say is 2 to the power of x, this what I wrote here, the same thing I wrote here, I can say this whatever unknown number 2 to the power of x must be between 6 and 4. Now I don't need to explain how I got from here to here. It's here already, okay? The same argument, the same reasoning. This has to be very clear to you. Please take time to really think about it and understand it. Okay? So from this inequality statement, you have to be able to write this. This is what it means. This unknown number, which is 2 to the power of x, is between 4 and 6. Now, you want to solve for x. X is in the power. Now you use your logarithms to bring the x down. So you can take log throughout the inequality. Now in an equation you have only 2 sides. This is a single inequality. In a single inequality you have 2 sides. This is a double inequality. You have 3. I can't call them sides. You have like three regions, right? 3 parts. So I take log on each part. Okay, so take log. We usually take ln, right? So let me write what I'm doing here. I'm take ln. on each thing. Okay, so that will give me ln 4 ln 2 to the power of x ln 6. Okay, now I can later, I'm not going to worry about what ln 4 and ln 6 are right now. I can do it in the end using the calculator. It's going to be some number. Ln 4 is a number, ln 6 is some number. Let me just write it as it is. Ln 4, I'm going to simplify this middle expression. Now I can, because I took ln, I can bring this x down to the front. So this is x ln 2, ln 6. Now I have to isolate x, right? I have to, in the end, get an inequality only for x. I need to isolate x. So what should I do now? Divide throughout by ln 2, this number. So let me write here what I'm doing. Divide by ln 2. Divide by ln 2. What does that give me? Ln 4 over ln 2. And when I divide the middle part by ln 2, I just get x. That's what I exactly need to happen. That's what exactly needs to happen. X is now isolated. And ln 6 on this side over ln 2. Now you can take the calculator and see what this number is. Okay? And that is, this is number 9. That is just 1. This is 1. And that is 2.58. Okay? Kavind, is it clear?
Yes, miss.
Okay.
Thank you.
Yes, ln 4 divided by ln 2 is 2, no, miss, in my cap.
What? No.
Miss, is this supposed to be ln 2 over ln 2?
Where ln 2?
Because 2 to the power of x is greater than 2 and less than 6.
Oh, it's 2. I'm sorry. I made a mistake. Yes. Oh, this is 2. Thank you. This is 2 now. I've made a mistake here. This is between 2 and 6, right? This number is, if I draw a number line again here, if you have 4 somewhere here, this number has to be, the distance between this number and 4 has to be less than 2. So it's 6 and 2. Sorry, I made a mistake. This has to be 2. This is 2. This is 2. This is 2. That's how you get 1. Okay. That's a mistake that I did.
Yes, why does your camera lag all the time?
Yeah, it's is that a big lag?
No,
Is that a lot? Like a few seconds. I don't know, because now it's not the it is the camera on the phone, so it has to come. It's you know, it happens through Wi-Fi. So what's on my phone camera? It's the phone camera that's capturing capturing this. It gets displayed on the computer screen, and that connection is via Wi-Fi. Sorry about that. I got stuck, right? Sorry about that. I was just talking. I didn't know that I was, my Zoom had gotten stuck. I didn't know. I was just talking. Okay. What I was saying, Malik, did you hear what I said? I don't know why there is a lag. Yeah.
It's okay, miss. It's okay.
I can try writing a little slower so that it can catch up with my voice.
No, miss, it's okay, right? You can write in your normal speed. There isn't a big, huge lag.
Okay. Okay. So do you have any more questions from this? If I go back to the homework sheet, what we just did was the 9th one, and the 10th one solution also I have put in the chat. It's gone now. Is the recording still happening? Let me check. Is the recording still happening?
Yes,
Because
miss.
it's happening now. Okay. Okay, so if that is okay, do you have any questions from the homework? Now I know, let me just say this. I can see that 10 of you are here now. When I started at 6:30, only 3 of you were here. Malit excused himself with a valid reason. If you're joining the session after I have started the class, you have to excuse yourself, okay, by dropping a message on the chat box. It's just like you walking into a class after I have started the class. You can't just walk in, you have to excuse. And let me know why you are late. I get very annoyed when you get late for an online session. You're at home. Unless you, for a valid reason like what Malit had, like a power cut or whatever. So that's why I always ask you to log in 5 minutes before the time that we start. Okay, Nathan. Yeah, whatever reason, you just let me know. Due to this, I got late. I'm just joining. You let me know when you join. Okay. Right. So if there are no questions from this, let us go back to our lesson. We were talking about how certain non-linear relationships could be turned into a linear relationship by using logarithms, right?
Miss, are we not doing practice paper 2?
Are doing. So what I thought of doing was the first hour we will continue the lesson, first hour and a half or so, and then last half an hour I will quickly go through the solutions of, not the answers of, the practice paper 1. Have you all done?
Okay, yeah, I did.
Okay. Is there anyone who did not do the paper, practice paper 2, P1 practice paper 2? Are you all ready with your answers for that? Because if you all haven't done it, it's pointless me just giving you the answers, because I want you to put marks and tell me how much you got. We are going to, okay, Sasindhu is ready. Is everyone ready with your, okay, Hatpi is ready with it, Malit is ready with it. Can I quickly know from everyone? Netli is very good. Others? Okay, Kavindi? Okay, so looks like I will not wait for all of you. So like majority of you are saying, okay, Thalindu, right. So let's quickly, because I want to finish this. Right, so we started the first, I said 2 types of relationships, curvy relationships. Curvy is not a very mathematical word. If I say non-linear, that means a relationship between X and Y that graphically is a curve. Okay, so I said that 2 types of curvy relationships or 2 types of non-linear relationships we can turn into linear relationships. What's the whole point of doing that? That enables us to find the unknowns in your relationship. This happens when you're actually trying to find an actual relationship between 2 physical quantities. So you would be taking some readings between these 2 quantities, maybe temperature and density. You take a couple of readings, and when you plot the graph, you can see that it's an exponential relationship. So you know that it takes this form. So you want to find a formula that connects these 2 quantities. So you know it has to take this form. It should be y equals some number times some number to the power of x, where x and y are your quantities. So how are you going to find what a and b are? That you can do, because from the curvy graph, the graph doesn't help you in finding this a and b. You know, but with a linear graph, the equation of a linear graph, the 2 numbers that you have in a linear graph, which is m and c, the gradient and intercept, are readily visible on the graph when you draw it, right? But for this, that's not the case. So we are going to see how we can turn these 2 the curvy or non-linear relationships into a straight line relationship, so that we are able to calculate or find a and b very easily from the graph. Okay. Okay, so we're turning a power relationship into a linear relationship. I hope you have written up to there. So let me take Okay, let me go to the writing pad. So this first point is turning a, first point, I'll put the bullet point, turning a, shall I start on a new page? It's easier. Turning a power relationship.
Aren't you showing the PDF?
Bimandi has a, okay, Bimandi. Malik, did you ask something?
Yes, miss. Why aren't you showing the PDF?
Because I'm going to write here.
So
This,
this is like a.
I'm going to do it here. I'm going to do it here.
Okay. Okay. No problem.
Turning a power relationship into a linear relationship. Is that what you have written? So let's start with, okay, if I go back to the PDF, the document a little bit, right? Turning a power relationship into a linear relationship. No, Nathan, you didn't miss any note. We are just starting the lesson now. You missed the homework. So, okay. So I will take what, this is the power relationship, right? Any power relationship takes that form. Now, first, take a moment. What are the two relationships we are trying to look at here? Which two nonlinear relationships are we trying to turn into linear relationships? Power and exponential. Make sure that you are very clear with the difference between the two. They look very similar. In a power relationship, y is equal to, you can have a coefficient. My a is the coefficient. Coefficient can be 1, right? It can be just x to the power of b with the coefficient 1. But there can be a coefficient. So to be fair, I have put an a in front. So some number, there can be a number. In a power relationship, you have x in the base. X to some fixed number like x squared, x cubed, x to the power of 4. Those are power functions or power relationships. Exponential relationship, you have x in the exponent. They look very similar. So that there you have y equals, again I put a coefficient a, some fixed number to the power of x. Can be 2 to the power of x, 3 to the power of x, 4 to the power of x, like that. Okay. So the first one we are looking at is a power relationship. So if you have a power relationship, y equals a x to the power of b in this form. Shall I write a and b in a different color? Because what we want to do is finally be able to, oh, sorry, I'm writing without sharing the screen. Okay. We want to be able to find these two constants. What is a here and what is b here, relating this x and y quantities. Okay. Now, you know, if you plot this, it's going to look like if you think of a quad, if b is 2x squared, it's going to be like that, right? You won't have the negative side, because for physical quantities, usually you don't have, like if you think of a lot of physical quantities are scalar quantities, you only have positive values, temperature, pressure, density, anything like that, right? They're all like positive side only. So you would have that positive part of the parabola. If it is x squared, x cubed still is like that. X to the power of 4 would still look like that slightly. So it's a curve, right? I'll finally show you how the general graph of that looks like. See what I'm going to do. I'm going to turn this into a linear relationship. That means I'm going to turn this into something in the form y equals mx plus c. That's what a linear relationship is, right? A linear function is. I'm going to turn this into the form y, the form, it's a form, okay, the template, y equals mx plus c. This is what I do. You just take log on both sides. Let me write it here. What am I going to do? I'm going to take log on both sides. Can be log or ln, doesn't matter, right? Log or, when I say log, I mean log any base. Log base 2, log base, any base, doesn't matter. So log base e is ln, right? But as I said, we usually like to work with log base 10 and log base e. That means just log and just ln. So let me say take log or ln. This means log base 10. When I don't specify the base, I mean that means base 10. This means base e. Okay, so take this on both sides. See what happens when I do this. Both sides. Okay, let's see what happens. So my y becomes log y. Shall I do log y or ln y? What are you comfortable? Are you okay with ln? Shall I write ln? Ln. Okay, ln y equals this side ln of this whole thing, a times x to the power of b. What have I done here? I have simply taken ln on both sides of my equation, my function formula. Okay. Now you can see that what you have on the left hand side is just ln y. Nothing you can't do for that. It's just ln y. I'll keep it like that. But the other side, I have ln the product of two things. There we have a rule with which we can simplify that. I hope you remember. I can write that as how? Ln
a plus
ln
ln x to the power of b.
Very good. Ln a plus ln x to the power of b. Okay, because this is like this something times something. Okay, I hope you remember the rule there. So I can separate them out as a sum. Ln a plus ln x to the power of b. And now this b I can bring in front. So let me write this. Ln y is equal to ln a plus b times ln x. Now, where are my variables? Where are my quantities? Shall I write the quantities? Shall I highlight the quantities? These are my x and y, okay? They were here earlier. Now they have gone into a long term. Ln y, ln x, okay? Those are my variables, like the quantities between which I'm trying to find the relationship. This ln a, now a is some constant. I don't know what a is, right? B is a constant. So ln a is going to be just a number, but I don't know what that number is. And b is just a number. Now, I'm going to just make a little rearrangement, okay? Ln y is equal to, I'm going to write this term here. That wouldn't make any difference, right? B times ln x plus ln a. I just, just rearranged it. Now this is what I'm going to do. If I call this ln y, this whole thing, as like some capital Y, I'm doing a little relabeling. Oh my God. I have been getting this call. I don't know why. Okay. I hope it's not something urgent. Okay, I'm sorry about that. Okay, come on. I'm going to relabel ln y as just capital Y. Okay, and relabel ln x as capital X. Do you see now this is falling into a form y equals mx plus c? Do you see it? I can call, this is a number, it's going to be my m, plus this is going to be, it's a number, it's going to be my c. Now what happens here is this. Now I will show you, okay? Now when you have this relationship, if you plot a graph for y versus x, so let me show you. If you do a, you can see now there. If you do a graph x, y versus x. So you will be plotting this, right? Y versus x. It's going to be some curve. It's going to be a curve like that. That's the curve you get for any power function. X squared, it's that one arm of the parabola. X cube, it's that one arm of the cube. You know, if you remember the cube graph, it's like that. That's one arm of that. X to the power of 4, it's not a parabola, but it takes a similar shape like that. I'm just drawing the positive side because usually you don't get negative sides for physical quantities. X, if X is a physical quantity, right? That's the curve you get for if you plot a graph for this. Y equals a x to the power of b. Yes.
Yes, if I feel like if you practically take this, it doesn't sound like b should be the gradient, no, miss, because like if you take something to the power x, if you change the base, wouldn't the gradient change instead of x itself? Here they are saying like the to the power is the gradient, but then shouldn't it be the other way around? It doesn't sound right now.
I don't understand what you're saying. What doesn't sound right? Shall I finish this? I'll show you.
Okay.
Let me finish it. Okay. Now, so if you plot a graph between y and x, it's going to be a curve because this is how x and y are related. But now if you plot a graph between, instead of x and y, if you plot a graph between ln y and ln x, so this is what I have called as y, right? And this is what I have called as x. So if you plot a graph of ln y versus ln x, that means, so suppose you have your x and y readings. X reading you will be taking from your experiment, xy readings. For each x reading you calculate ln x. For each y reading you calculate ln y, and then you plot the graph for ln y against ln x, and that graph is going to be a straight line, like, because this is how ln y and ln a is like a some straight line like that. Okay, that is y is equal to, sorry, this is ln y is equal to b ln x plus ln a.
Okay, miss, now I understood.
You understand?
Yeah.
Right? Now, so like this is your y, like I have shown you. This is your m, that is your x, that's your c. Now, if you just have to read that intercept, and that is equal to ln a, and you can compute what a is from that. And you can, from your graph, you can compute, you can, measure some y and x and like calculate the gradient, and that is exactly equal to b. You are able to find your a and b from the graph. So from this graph, intercept is equal to ln a. So intercept is just a number. When you read that from the graph, you put that number here, and you can compute what a is, and the gradient is b. Gradient is b. Okay, m is what b is. So turning this power relationship into a linear relationship using logarithms enables you to, using the graph, enables you to calculate your unknown constants A and B that are relating your two physical quantities. Is this clear? Clear, okay. Can you all copy this? So I will first copy this part, turning it into from here to here. I am wondering whether I'm getting a lot of, looks like I'm getting a lot of messages. I'm wondering whether it's something urgent. I can't take, because it's, I can't take the phone to check the messages. Okay, can you all copy? After you copy, maybe I will just quickly check what's going on. If you are done with that part, I will move this a little up. Is that okay? I'm moving this a little upward so that you can see the graphs. So the curvy graph we turned into a linear graph. This curvy relationship we turned into a linear relationship. Then from that linear graph, I can't take the phone, Hatti, because it's the this writing pad that you are seeing here. It's using the phone camera. It's the phone that's doing this. Like after you copy this, I will quickly check the messages. Can I move the paper a bit more upward? Like
Okay,
that?
miss.
Okay, up to here. So you so finally this is what enables you to two features of the graph, intercept and gradient. Simply intercept and gradient lets you find what A and B are, because intercept is equal to ln A and gradient is equal to B. So we'll do an example after we complete the full theory part here. Let me know when you are done. Okay, Bimandi is done. Okay, Nethni is done too. Shall I quickly show you now the other one? Nathan is done too. So it's the same thing that we do to turn an exponential relationship into a linear relationship. The same thing happens. So even you can do it on your own now. The next part of the note for the second bullet point, turning an exponential relationship into a linear relationship, same thing. Okay, but I will do it with you. But if you think it's going to be the same, you start with the exponential relationship, take ln on both sides. You will have to rearrange the terms a little bit to get that form y equals mx plus c, and you can again do a similar thing that would enable you to find those two constants. Okay, so let me, before I start that, I will just can you give me a moment? I will go to this slide. I don't know. Give me a moment. Okay, I'll quickly check my. I'll just mute. Nothing urgent. I'm sorry. There is slightly something urgent, but that can wait. That can wait. That can wait. No worries. So let's go back to the second bullet point, just like you have here. So you wrote everything under this. The second bullet point, you write the next bullet point, turning an exponential relationship into a linear relationship. Okay, I'll write that on the paper as well. Will you write it there? The second bullet point, turning an exponential relationship into a linear relationship. Okay, so that means one in this form, right? One in that form. So let's see how we do that. Okay, there you have. So I will start with, just like I did before, I will start with now an exponential relationship between y and x. Come on, so many messages. Y is equal to an exponential relationship. You might have a coefficient in front, some a times, some b to the power of x, some b to the power of x. X is in the exponent, okay? Right, we do the same thing. We take ln on both sides, ln or log. Take log or ln on both sides. What do we get then? We get message. There's a message from you. Miss, was this method derived by a single mathematician? Good question, Hatvi. I really don't know. I don't know the history about this. Something interesting to find out, isn't it? Let me. No, I don't. I don't think I have ever looked into the history of this this theory part. Logarithms has a long history, but using logarithms to turn a curve relationship into a linear relationship, I did that. Okay, good question. I hope one of you might be able to find it. You just have to Google it, right? It's very easy to find things now. So you do ln y equals ln a times b to the power of x, right? Very clear. We have a similar thing going on like the earlier case. Let me just go on to simplify this. Ln y on this side. This is a ln of a product. I can write it as ln a plus ln b to the power of x, and then I can ln a plus this x I can bring to the front as the coefficient of this. It becomes like that. Now, where have my y and x ended? In the earlier case, my y and x ended up being in a ln term. Remember? Both x and y. My y ended up in a ln term. My x ended up in a ln term. I got ln y and ln x. But here, my y has ended up inside a ln term, but my x is sitting nicely just as just a normal x. Okay? Now let me can you see mx plus y equals mx plus c form? Here you go. You just have to make a little rearrangement. Ln y, that have to be relabeled. That we will relabel as capital Y or something. Mx, this is going to be my m. X is already there. So let me write it as ln b. It's just a number, remember. Ln b is just a number. M, that could be your m. X plus ln a. Do you see the form now? I can call this. That has to be changed into a different label because it's ln y. So it's capital Y. Like you have to relabel it. This is your m. X, you can just take it as x. I mean, it's just x already. Nothing has happened to that, right? X is just still simple x. Plus, that is your c. It did turn into a linear relationship, okay? So if you look at the graph of this, let me show you the graph of the exponential relationship first here. So your exponential relationship, y versus x, you know, exponential relationship goes like, any exponential relationship goes like that. It starts at 1, right? So, oops, sorry, you can't see the whole thing, right? Okay, like that, okay? That's remember the exponential graph, okay? All exponential graphs go like that. I'm not drawing the negative side. It continues like that, but I'm not drawing it because for physical quantities, you are not going to get that negative side. And so this is y equals a times b to the power of x graph, how that looks like. Whatever a and b are, it'll look like that, right? So if a is like a number 5, this would be 5. It might be 5, but we can't be sure. It will be 5 actually, or let me not say it. I will let you think about that. So it looks like a can be actually found out from the graph, but not b. But let's see if I plot the graph of that now. What does that mean? I have to sketch what versus what. I have to change my y-axis to ln y. So again, if you think of having a set of actual experimental data, readings. Okay, Nathan, yeah, thank you for that, but let's not read that now. Anyone can read it later, everyone, not now. Nathan, I didn't mean you to Google it now. Did you miss anything that I'm explaining?
No, miss.
Okay.
I heard everything.
Okay.
Miss, I have a question. It's just a question I want to know. What's this? Why did people, instead of using like the angles, why did they turn into radians?
Radian is just another unit.
Yeah, miss, why did they? Why?
Because when you measure angles in radians, it makes a lot of calculations really, really easy. You saw this when you learned the formulas for sector area and arc length, how the formulas got simplified. Just like that, a lot of other applications become simple when you measure your angle in radians. Like go back and think in your O levels, the two formulas you had for sector area and arc length when you were measuring angles in degrees, the formulas you had. But if you measure your angles in radians, the formulas became very simple. That's just an example. That's the only example that you have learned so far that I can show you. But there are so many other places, applications, when it comes to applications of angles. If you measure your angles in radians, your computations become very simple. Another connection you can see like this: the area and circumference formulas of a circle involves pi, and when you measure angles in radians, you have pi in them, so they get simplified easily when you work with circles. So there are a lot of places where that helps in your computations and simplifications. It becomes simpler when you measure your angle in radians. Okay, so back to this. Okay.
Okay, fine.
Okay.
Thank you, miss.
You're welcome. We'll now that's a question out of what we are doing now. So you should leave such questions to ask like not in the middle of the middle of this, Nathan. Okay. So now what I have to plot this graph between ln y versus, should I change my x-axis, x into something else? No, I can keep it as x. It is x, right? And then that ln y versus x graph would be a straight line. I'm always drawing something like that, but it could be some straight line, like it could be a straight line this way. So that's what you get when you do ln y equals, ln bx plus ln a. And from this graph again, intercept is equal to ln a, and you can find a from that. And gradient is equal to ln b, and you can find b from that. That's how you can find both a and b from the linear graph that you derived out of the curvy exponential graph or the relationship. So you turned this into that by turning this relationship into that relationship. Okay. When we look at an actual example, you will this will become more clear. This is just the theory part I showed you. Okay, let's look at an example. Now 1 hour is gone. Can you quickly copy this? We'll look at an example. We'll clarify this and then we will start discussing the P1 paper. Okay, can you start copying this? So x stays as it is here. X is x. Okay, if you have come to the bottom of that algebraic part, let me move this up. I hope that is okay, so that you can see everything now. Okay, Nethi and Bimandi, as usual, are done. Can I assume everyone is done? If Malit is done, usually that's
No.
Nathan, you are still doing. Okay, still copying. While others are copying, girls, girls, you're working fast, isn't it? Do you have any questions till the others finish? Any questions from this?
Done.
Okay, Nathan is done. Does anyone have any questions from what we just did? Anything that is not clear? Okay. Then shall we look at an example where this is used? Okay. Your textbook has 2 questions. I will show it in this on the screen. I'm going to change the screen now. Hope that is okay. Here's your first example. I'm going back to this. I have one example somewhere down here. Oh, it's down here. Oops, where is it? Oh, right there. Okay. This is a past paper question. This is in your book as well, but I'm showing the question on the screen, so you can just look at this. So you write exercise, okay? Exercise, and shall we try to do this question? Okay. So they have given you a graph here. First, look at the axes. Y-axis is ln y, x-axis is x itself. So you know out of the two, which kind of a relationship the x and y must be having here? An exponential relationship. It's in an exponential relationship that x ends up just as x without being in a long term, isn't it? So even if you don't know that, it's fine. Okay, so they have given you the transformed graph. They have plotted it for you. So let's read this and see. It says the variables x and y satisfy the equation y equals capital A times simple b to the power of minus x. Okay, don't worry, your x is minus there, don't worry about that, where a and b are constants. The graph of ln y against x is a straight line passing. So they have given you 2 points. They have given you the intercept and 2 points so that you can calculate the gradient, right? Straight line passing through the points this and this, as shown in the diagram. Find the values a and b, corrected 2 decimal places. Okay. Can you all sketch this graph and write the relationship and mark the 2 points? Just do that until I also do it on the paper, and then we'll work on the solution together. Okay. So the graph, so we'll all copy this into our papers or books or whatever. So the graph goes like that. So it's ln y against x, and it goes like, it's like that. They've given this point here, 0, 1.3, and a point somewhere here. Also they have given 1.6, 1.6, 0.9. Okay, and the relationship is given as y is equal to capital A b to the power of minus x. Okay. Okay. You don't have to copy the whole question. It's in your books. I'm not very sure what page number it is in your book. So if you look at your logarithms chapter, you can find this question in a certain I can tell you the exercise 2C. Okay, it's on exercise 2C. In my book, it's page 49, but your books, it must be a different page. If you're ready with the graph and the equation, I will go to the document, the writing pad. And let's start working on it. We are supposed to find capital A and B, the two constants, A and B. So I'm showing you the graph here. And here's the the actual relationship between A and B. We are going to transform this into a linear one using logarithms. Now they have turned it, they have used ln, so you have to take ln on both sides. Let's just do it. Let's take ln on both sides. You just have to do it here again and see what this turned into. Okay, so let's take ln on both sides. Let's do it together. Ln y equals ln a times b to the power of minus x. Then the right hand side I will simplify. Ln y is equal to, I can break this down as ln a plus ln simple b to the power of minus x. Next I can do, nothing would change here, ln a. I can bring this minus x to the front here. It will become minus x ln b. Now I will just put it into the format by just rearranging my terms. Ln y, I'm going to write this in front. So minus, and I'm going to put the ln b first. That's going to be my m x plus ln a. Do you see it has a negative gradient? That's why the line is this way. Now let's
excuse me, Miss.
Nathan.
Miss, instead of putting that is minus ln b, can't we put it as minus x? I mean, it's like the x is a minus, but the ln b is a positive.
That means your gradient is negative, no, Nathan? This is your gradient. Your
right, because the line is descending, right.
Yes. So you have to minus sign. I mean, if you have what do you mean by x is minus? So that minus sign can be thought of as belonging to the number here, because it's a gradient that is negative. And this is your c. You just need to identify what m and c are. Now don't circle this. That's a mistake. Okay. So like their graph is ln y versus x. Then this has to be the gradient. That has to be the c. Okay. So you can read both m and c. You can read c from the graph. You can calculate m by using the 2 points given, and you can find this a and b. Let's use, shall we use this first? What is c from the graph? Let me write. From the graph, I know that c is equal to what? C is equal to 1.3. C is 1.3. Okay. Then I know 1.3 is equal to ln a. C is ln a. 1.3 is equal to ln a. Now how do I solve this for a? A is my unknown. How do I solve for a here? What can I do? To get rid of ln, what can I do here? There are two ways of thinking about this. In order to solve this now for a, there are two things that you can do. I will show you both. I will leave you to choose whatever the method that fits you. Okay. First method, So I'm trying to solve this, okay? Method 1. I mean, it's not even, it's so simple. I'm just writing method 1, method 2. There's nothing much. Okay, let me start with the equation I have. Shall I write it this way? Ln A equals 1.3. I can convert this into to an exponential statement. Remember, any logarithmic statement can be written as an exponential statement. If you go back to your note, we have learned that on the maybe the first or the second day of this lesson, of this topic. Any log statement can be written as an equivalent exponential statement and vice versa. So this means e to the power of the base is e to that power is equal to a. That's what it means. See whether you remember this. Turning a log statement into an exponential statement and vice versa. Do you all remember that? This is the base. This is the I'll show you this. Would you remember? I don't know whether I have to be able to see. I don't know whether you see this, but right on top, what you have on this page, this. This and that. Hope you remember that. Oh, Tarindu is saying, I'm a bit confused about the, Tarindu is saying, Tarindu is a bit confused about the y equals mx plus c format. Shouldn't there be y alone? Yes, Tarindu. Wait, here, this is your y. This is your different y. I can't again call it y. Y. This is my simple y. If I call that whole thing as like capital Y, here the graph has been drawn. The graph has been drawn by taking ln y as your y axis. Is that not clear? So it's a different, I mean, it's a, your x and y are your readings or your quantities. You have to find ln y of those readings and then plot against non-y and x for this particular one. Tarindu, if you can like talk to me like just, you sure? That ln y you call as your new big Y. Okay. Please ask like that, because this can be, I mean, it's a new thing that we are doing here, right? Can we do that? Yeah, we can do that. You're welcome, Tarindu. So is this clear to everyone how I wrote this from that? I don't know whether you have forgotten that. Okay. So immediately then a is e to the power of 1.3. You compute that with your calculator. A is whatever e to the power of 1.3. The second method of doing this is, if I start with the equation again, ln a equals 1.3. Because I have a ln here, I can use the inverse relationship between ln and exponentials to get rid of ln. It's like if I have a square, to get rid of square, I square root, right? If I have a square root of x, to get to x, to get rid of the square root, I square, right? You're familiar with this. Oh, okay, Tarindu, right? We can do the same thing here. To get rid of this ln, the inverse of ln is taking a power of e. So what I can do is raise both sides of this equation to a power of e. I raise both sides to a power of e. This is how it looks like. E to the power of ln a. Ln a will go to the power. And e to the power of 1.3, the two sides are raised to the power of e. Okay, Hatvi is saying he didn't understand the method 1. I'll come back to it after I explain this. See whether this is okay. I actually prefer this method that I'm explaining now, method 2. Because to get rid of ln, you are raising to the power of e. If you have e, you take ln to get rid of e. The inverse property we are using here. Okay, so I have raised both sides to a power of e. Why did I choose e? Because my log was ln. My base of the log was e. So we converted a curve to a straight line, didn't we? Yes, we did. Then miss, is it something like differentiation? No. Why is it? Why should it be? Where did differentiation come from? Why do you think it's like differentiation? When you differentiate a function, you are finding how the gradient along that function is changing. If we differentiate a squared curve, we get a straight line. Of course, that is because the gradient along a parabola, the way the gradient is changing along a parabola is a straight line. But when you differentiate, that's a different function. And that function doesn't tell you anything about the original function. There are two different functions, original function and the derivative function, right? We call them. That's true. I mean, you can, but it's not the same function became a straight line. It's a different function now. It's a derivative function. Like, but for a cube, x cube, when you differentiate it, that's not a straight line then. It's only for a parabola. For a quadratic, when you differentiate, the derivative function of a parabolic function is a straight line. It's a different function. This is on the other hand, it's another way of, it's the same relationship. We have just done a little manipulation. It's the same relationship manipulated into a straight line relationship by changing x and y accordingly, appropriately. Like this, guys. Yes, Vasant. I'm sorry, I'm saying Vasant because I'm seeing your name as Vasant. Yes, Taridu. This is an exponential relationship in this, guys. It's there. You have like manipulated it into something that looks like a straight line. Behind it is actually an exponential relationship. We strategically done something to transform it into a straight line. It's the same relationship. The relationship between x and y is exponential. The relationship between x and ln y is linear. Okay? Shall we go back to this now? So I'm showing you the second method of solving this in order to find a. I read the intercept from the graph 1.3. Now I just have to compute a. It's a little computation. I said you can do it this way. I will explain that for Hatvi a little later. Method 2 is to just raise both sides to a power of e, and ln, when you have like this is a logarithmic rule, not logarithmic rule. We did this as a rule. These are inverses happening together, so they cancel off each other. E to a power of ln cancel out. You get just a here. So a is e to the power of 1.3, and you can just find it using the calculator. Now Hatpi said he didn't understand this. Yeah. Let me go back. Let me take a different. This is from. Okay, let's take a solid example. If you have 2 to the power of 3 is 8, this is an exponential statement. Does everyone understand the statement? 2 to the power of 3 is 8. The same statement I can write as a log statement. The same relationship I can say log base 2 8 is equal to 3. This is an exponential statement, EXP statement. This is a log statement. They are the same thing. It's saying the same thing. It's like if I say an addition statement. 3 plus 2 equals 5. It's an addition statement. This is an addition statement. I can say the same thing using a subtraction statement. If I say 5 minus 3 is 2, I'm the same 3 numbers. I'm putting in it's the same thing, but I've turned it into a subtraction statement. Subtraction. Still the same thing. So any log statement can be turned into that. Any exponential statement can be turned into that. Hatvi, that's what we did here. So ln means log base e. So e to the power of 1.3 is equal to a. Okay, nice. Okay, any more questions? Which method do you prefer? I like this one. You can just raise both sides to the power of e. Then e and ln get like, don't cancel it like that, the way I did. It's not like that kind of cancellation. It's because they are inverses, they get cancelled. Okay, it's like doing and undoing. But the e to the power does get undone by ln. So the effect gets cancelled and you just get a here. This a, you just get a here. Because ln has been taken off a and that has been raised to a power of e, then you are back to your a. So you have your a. What's the a answer? What is e to the power of 1.3? You have to use your calculators for that. So I will leave that to you. Now to find b, you need the gradient. Gradient is equal to, okay, 3.67. 3.67 is your a. 3.67. Now to find b, you need the gradient. Okay, what is m? So again from the graph, m is, you are given 2 points, coordinates of 2 points. Let's calculate m. 1.3 minus 0.9 over 0 minus 1.6. You get a negative gradient. How much is that? Can you find? So Miss, b will be 1.28, which is e to the power of 0.25. Is the Nethni? First of all, what did you get for m? M is minus 0.25 minus 0.25. Then what you do is, so we know that m is equal to from here, gradient is equal to minus ln b. So minus 0.25 is equal to minus ln b. Sorry, there was a huge lag. You can raise both sides to the power of e. E to the power of 0.25 equals e to the power of ln b. That is, b is equal to e to the power of, that is correct, Nathni. Yes, you're correct. So b is e to the power of 0.25, which is how much? Yes, Malika. 1.28. 1.28. B is 1.28. Okay, yes, Malik, that's right. Did you understand? We will do one more now. The thing is, it's 8. I don't want to like finish without finishing this completely. I don't want to start the P1, discussing the P1 paper. We'll do one more question, one more example, exercise. Which one do I take? I can do this. Shall
Miss, can you go back? Miss, can you go back to that exercise, Miss, the previous one?
Yeah.
I'm still copying it.
Let me know when you are done.
Done, Miss. Thank you.
Has everyone copied? Everyone has copied, right? I hope everyone is done copying this. So I'll go back to this again. Here's another exam question, past paper question. I'm going to let you do it on your own now. Very similar, do you see? Very similar to that, but here the graph is ln y versus ln x. So it's the power function. I mean, you don't have to know what it is. Just do it. You will. You don't have to recognize when you see, is this coming from a power function or is it coming from a? You don't have to know. You don't have to recognize like that. You just take the relationship they have given, take ln on both sides, and just find the constants. Can you quickly do this on your own? So it says the variables x and y satisfy the equation y equals k x to the power of a. So it's a power function, power relationship, where k and a are constants. The graph of ln y against ln x is a straight line. So y versus x would be a curve. Ln y versus ln x is a straight line. Okay, it's a straight line passing through the 2 points given, just like the one before, as shown. Find the values of k and a. Correct to 3 significant figures. Quickly do it. And I will also do it. And finally, I will show you my work. Okay, we can compare. if someone finds the gradient, let me know on the chat what you get for the gradient. Okay, gradient using these 2 points. If you have found the gradient, tell me what that is. Minus 1.3. Thank you, Hatsi. Now, I hope you can see that the intercept is not given in the sketch they have drawn. In the earlier one, the intercept, the coordinates of the intercept had been given. Here, it's not given. Oh, what have you found? I am still finding, and I don't have a calculator. So let's wait. I'll tell you. Yeah, your A is right. Malik, your A is right. You have to calculate the intercept. You have to calculate. What is wrong? Your K is wrong. Huh? Okay. Your A is right. Did anyone calculate C? First, you have to calculate C to compare it with whatever that you get here to find K. Can you tell me what C is first, Malik? Intercept. What's the intercept you got? Does anyone have the intercept? After calculating the gradient, you can put it into the form y equals mx plus c, use one of the pair of coordinates given, plug it in and find c. That's how you find c, right? That's O-level work, O-level knowledge. When you know the gradient of a graph and if you know a point on the graph, on the line, you can find c. Is that c beyond b? Is that the grade? Is that this intercept or is that the value? Okay, intercept. Then when Bimandi is k, I will just is this what you got, Bimandi? I'm asking because I can't ask out loud to ruin. I don't want to ruin other people's work. Is that what you got for k? Whatever that is, I don't have a calculator. Shame, na? Okay, shall I take you to the writing pad? Now you must have worked this out to some extent. So let us compare our work, okay? Here's my work. The first thing I did was, so I took the relationship they had given. Okay, Vimandi. The relationship they had given was this. It's an exponential relationship. You don't even have to know what it is, right? So you take ln on both sides. You work your way through this. So you simplify this, you break it down into 2. You bring the a to the front. And then you rearrange to give the form y equals mx plus c. Ln y has to be called some capital Y. You have to give it a new label. Your a is your m. Ln x is your new capital X. Because the graph has been drawn. Ln y versus ln x. Your new y is ln y. Your new x is ln x. And ln k is your k. So I have first written down the 2 relationships. My gradient m is a. The intercept is ln k. Right? So first I worked with the gradient because I can easily find it from the 2 points given. So using the graph, I calculated m. M is, that's the intercept. What is intercept? 4.27. Yeah, 4.26 or 27. Yes, Hakti, that's right. Right, so for so for the gradient you get minus 1.39. So gradient is a, so a is minus 1.39. That's your a. And then you have to use your gradient. Now the intercept cannot be read off of the graph because it's not given. So you have to put it into this relationship. So it's capital Y equals m. M is this, x plus c. You use one of the points to substitute and find c. C is 4.26 or 4.27 maybe. I've used Biman this intercept, 4.26. And then intercept is equal to ln k. Then you solve for k. So k is e to the power of 4.26. How much is that? How much is that? How much is k? What's the answer? E to the power of 4.26. Is it right? So 70? 71.2 is the k value. Your answers have to be to 3 significant figures. Is that clear?